Have you ever wished your smartwatch could be as thin as a sticker? Or that your jacket could charge your phone while you wear it? These amazing ideas are closer to reality than you might think, and it's all thanks to a new kind of power source: flexible batteries. For a very long time, batteries have been hard, solid blocks. Think about the battery in your phone or the one in a TV remote. They are rigid and heavy, which makes them difficult to use in devices that need to be soft, wearable, or change their shape. As our gadgets get smaller and more integrated into our daily lives, we need power sources that can keep up with these new designs. The demand for flexible power is growing every single day. We are entering an era of wearable technology, where electronics are not just things we carry, but things we wear. Smartwatches, fitness trackers, and even medical sensors that stick to our skin all need batteries. If these devices are going to be comfortable and practical, their power source must be able to bend, stretch, and move with our bodies. Rigid batteries just don't work for this. They create bulky, awkward designs. This is why scientists and engineers are working so hard to reinvent the battery, transforming it from a clunky box into something as flexible as fabric or a piece of paper. Imagine a world full of bendable electronics. Think of a tablet so flexible you can roll it up like a newspaper, or medical bandages that can monitor a wound and deliver medicine, all powered by a battery embedded within the fabric. These aren't just science fiction concepts anymore. The key to unlocking this future is developing batteries that can be twisted, folded, and even stretched without breaking or losing their ability to hold a charge. This is a huge engineering challenge, but it is one that researchers are tackling with incredible creativity, leading to some truly innovative designs that are changing how we think about energy storage. So, why is this so important right now? It's because the Internet of Things, or IoT, is expanding rapidly. This is the idea that everyday objects, from our shoes to our coffee mugs, can be connected to the Internet. To make this happen, each object needs a tiny, long-lasting power source that can fit into any shape imaginable. Rigid, heavy batteries are the biggest bottleneck holding back the full potential of wearable tech and the IoT. By solving the flexible battery puzzle, we open the door to a whole new generation of smart devices that will seamlessly blend into our lives, making them more convenient, connected, and amazing. When it comes to designing flexible batteries, scientists are exploring two main approaches, each with its own unique strengths. The first type is the two-dimensional, or 2D, planar battery. Imagine a very, very thin sandwich. That's essentially what a 2D planar battery is. It has layers of materials, an anode, a cathode, and a separator in between, all laid out on a flat, flexible surface. This thin, sheet-like structure allows the battery to be bent or even folded without breaking the internal connections. Scientists have been incredibly creative with this design, even taking inspiration from the ancient art of origami to create batteries that can be folded into complex, compact shapes. These 2D batteries are perfect for devices that need a flat power source, like a flexible smartphone screen or a smart credit card with a digital display. The materials used are often based on lithium-ion chemistry, similar to the battery in your phone, but they are applied as thin films or inks onto a flexible substrate, like plastic or even paper. This method allows for a lot of design freedom. For example, a battery could be shaped to fit perfectly around the curve of a smartwatch or integrated directly into the casing of a flexible tablet. The planar design is a logical first step in moving away from rigid batteries towards something more adaptable. The second, and perhaps even more futuristic approach is the one-dimensional, or 1D, fiber battery. Instead of a flat sheet, imagine a battery that is as thin and long as a piece of thread. These fiber batteries are created by building the battery's core components, the anode, cathode, and electrolyte, concentrically around a central fiber, or by twisting multiple material-coated fibers together. This creates a power source that is not only flexible, but can also be woven, sewn, or knitted directly into textiles. This is a game changer for smart clothing, turning an entire garment into a distributed power source without adding any noticeable bulk or stiffness. This revolutionary 1D structure opens up a world of possibilities that are simply impossible with 2D batteries. Think of a soldier's uniform that powers communication gear, a firefighter's jacket with integrated sensors, or a fitness shirt that monitors your vitals and charges itself with your movement. Because fiber batteries can be made incredibly long, they can be integrated seamlessly into fabrics, distributing the battery's weight and function over a large area. The materials often involve lightweight carbon nanotubes and polymer gels, which contribute to their flexibility and safety, making them ideal for next-to-skin applications where comfort is key. While the ideas for flexible batteries are exciting, scientists and engineers still have several big challenges to overcome before they become commonplace in our gadgets and clothes. One of the most significant hurdles is safety. Traditional lithium-ion batteries contain flammable liquid electrolytes. If a rigid battery in your phone is punctured, it can be dangerous. Now, imagine that battery is flexible and woven into the shirt you are wearing. Any leak or short circuit could pose a direct risk to the wearer. Researchers are working hard to solve this by developing solid-state or gel-based electrolytes that are not flammable and are much more stable, even when bent or stretched. Another major challenge is durability and performance over time. A battery that is constantly being folded, twisted, and stretched will experience a lot of physical stress. This mechanical strain can cause tiny cracks to form in the battery's materials, which can reduce its ability to hold a charge or even cause it to fail completely. Scientists need to find materials that are not only flexible, but also incredibly resilient. They are experimenting with self-healing polymers and robust nanomaterials that can withstand thousands of bending and stretching cycles without degrading. The goal is to create a flexible battery that lasts just as long, if not longer, than its rigid counterparts. Manufacturing these batteries on a large scale is also a puzzle that needs to be solved. The methods used to create prototypes in a laboratory are often slow and expensive, involving precise, layer-by-layer deposition of materials. To make flexible batteries affordable enough for consumer products, we need to develop new manufacturing techniques. Researchers are looking into processes like roll-to-roll printing, which is similar to how newspapers are printed, to produce large sheets of 2D batteries quickly. For 1D fiber batteries, they are developing methods to spin long, continuous battery fibers that can be spooled like regular thread, ready for textile manufacturing. Finally, there's the issue of energy density. This term simply refers to how much power a battery can store in a given size or weight. Right now, many flexible battery designs have a lower energy density than the rigid batteries we are used to. This means a flexible battery of the same size might not be able to power your device for as long. The challenge is to increase the energy density without sacrificing flexibility or safety. This involves discovering new electrode materials and optimizing the battery's internal structure to pack more power into a smaller, more flexible package, ensuring our future wearable devices can run all day long. Despite the challenges, the future for flexible batteries looks incredibly bright. The pace of innovation in this field is truly astonishing, with researchers around the world making breakthroughs every year. We are moving beyond simple proof-of-concept designs and are now focusing on creating practical, high-performance batteries that can be manufactured efficiently. The collaboration between material scientists, chemists, and engineers is leading to creative solutions for problems like safety and durability. For instance, new water and salt electrolytes are emerging that are non-flammable and can improve battery longevity, directly addressing key safety concerns for wearable technology. The potential applications for this technology are almost limitless and will fundamentally change our relationship with electronics. In the medical field, flexible batteries will power implantable devices that can monitor health from inside the body, or smart bandages that can accelerate healing. In consumer electronics, we can look forward to phones that fold into tiny squares, laptops that roll up into a tube, and clothing that intelligently adapts to our needs. These devices will be more intuitive, comfortable, and seamlessly integrated into the fabric of our lives, all powered by energy sources that move and bend just like we do. The development of 1D and 2D flexible batteries is not just an incremental improvement, it represents a paradigm shift in how we design and build electronic devices. For decades, the rigid battery has dictated the form factor of our gadgets. Product designers have always had to work around a solid rectangular block of power. By freeing the battery from this constraint, we are giving designers a whole new level of creative freedom. Soon, the power source will no longer be a limitation, but another flexible component that can be molded into any shape, enabling a new wave of products that we can't even imagine today. Ultimately, the journey toward a fully flexible electronic world is well underway. The ongoing research is not just about making our current devices bendy. It's about creating entirely new possibilities. As scientists continue to refine materials, improve manufacturing processes, and boost energy density, We will see flexible batteries move from the research lab into the products we use every day. The path is clear and the commitment is strong. The next generation of technology will be soft, wearable, and powered by batteries that are as dynamic and adaptable as the world around us, heralding a truly bright and bendable future.